Lesson 5, first of all, or number 5, Dylan, this is kind of strangely written, the fact that it goes left and right, but I said, you know what? What we're really doing is we're clearly shaking hands here and meeting up there. What I actually did, because my brain visualizes better, I quickly resketched this. I said, okay, I've got a battery. Everyone goes through the 2 ohm, and then instead of going left and right, I went to the right and split up there, because we're splitting up, and I said we're splitting up into a 6 ohm, and that'll get us to the bottom of the chairlift. Is that okay? And I said, you know what, those 2 resistors to the left are in series. That's the same as 1 8 ohm, but that'll get us also to the bottom of the chairlift. So far, so good? Yeah. I said, okay, these 2 are in parallel. You see where the 8 came from? All right, 3 and 5. Those 2, when I combine them, are in parallel. So I said, you know, 1 over 6 plus 1 over 8 equals 1 over R parallel. 1 over 6 plus 1 over 8 reciprocal. 3.42. I can combine these guys as one single solitary 3.42 ohm resistor, which then led me to say, you know what? The total resistance is 5.42. You see where that came from, Dylan? Yeah. I added the 2, which is in series. I said, okay, I got that. Well, now that I got R total, I total is going to be V total divided by R total. It's going to be, what's my total voltage? 20 divided by 5.42. And I was getting yucky numbers, but whatever. I glanced at my answer. I noticed it had a decimal, so I'm not going to freak out. I said 20 divided by that. Looks like the total current is 3.68421. I'll go 3.684. Now I went back to my original circuit. Said, okay, what's the current going through the 2 ohm resistor? All of it. Oh, how big? 3 point, what did I say? Then I said, oh, I also know the voltage I lose going through that. It's I times R. It's that number times 2. I said, I guess I lose 7.368 volts. And the question just fell apart because, Dylan, can I ski this run here and get back to the bottom of the chairlift? Yeah. How high is the chairlift? What do I lose going down that hill? How much must I lose going down that hill? 20 minus whatever's left has got to be how high that hill is. That hill is 12.6315785 volts high. 12.6. Oh, now that I know that, I can find the current in the 1 ohm in the 6 ohm resistor, or the power in the 6 ohm resistor, or whatever. But they didn't ask that. That's how I think I'd handle that. And I think what was confusing was the way the diagram was done. But yeah, I worked around it. Vlad. Yeah. Right away, I zoomed in on the resistor where they told me 2 things. Because if they told me that it's 25 and 3, I also know that it's 75 volts. And for what it's worth, this is the same as one 15 ohm resistor, and I know it has to have 75 volts. Yes? Yep. Oh, so I know that it must have 3, Mr. Duick, 75 divided by 15. It must contain 5 amps. Now, if I break it up into its 2 hills, the 10 ohm and the 5 ohm, I don't know what the voltage is in each of those hills, but I can tell you it's got to be 5 amps and 5 amps because there's nowhere else for those skiers to go. Oh, which means I can now calculate the total current. What's the total current? So what's the current up here? 8 amps. What's the voltage in that top one? 160 volts. So if I walk that path, looks like I get 235 volts high. Is that okay?
Yep.
Any others?
Number 8, the last one you assigned.
Did you just get the notes for me?
Yeah.
Have you tried this yet? So try it first, please.
No, I meant like, that was the last one you assigned.
Oh, was number 8 the last one I assigned?
Yeah.
Oh, yeah. Thought you. When I say any others and you say number 8, the last one you assigned, I go, okay. Any others going once, going twice? Oh, we got some late humans. So, skipping lesson 6 temporarily, I may come back to it. Lesson 6 is actually an extension. We look at, hey, what if you have more than one battery in a circuit? And it explains why in flashlights the batteries are end to end, but in your calculators the batteries are side by side, parallel or series. We'll talk about that a little bit. But lesson 7, this is what I'll be really assessing you on. Terminal voltage. Up until now, Rob, we've been slightly inaccurate. You see, actually, every single circuit that I've given you, I've been missing something. Every single battery has an internal resistance. Graydon, there is no such thing as a perfect battery. There is no such thing as a perfect battery. In real life, you actually lose a tiny bit of voltage traveling through the battery. So if your battery says 6 volts on the side of it, I guarantee you're not getting 6 volts. If your battery says 1.5 volts on the side, I guarantee you're not getting 1.5 volts. We call the actual measured voltage that you're actually getting, that's the terminal voltage, because that's the voltage between the two terminals. So read along with me, please. It says this. Terminal voltage. This is the voltage or potential difference between the ends of a battery or cell. The ends or posts of a battery are called terminals. A cell contributes some resistance to a circuit. This is called the internal resistance of the cell. In terms of a circuit drawing, so here's my diagram of a standard battery. What you have is this right here. This is called the EMF. The EMF. And what this is the maximum theoretical voltage. Printed on the side of the battery. In fact, so far what I've usually been doing, well, we'll come back to that. And Cole, it's constant. It doesn't change. Because when you take a battery out of one circuit and you put it into a different circuit, the writing on the side of the battery doesn't change. What does change is the actual voltage you get, not the theoretical voltage. The theoretical voltage, by the way, EMF with that funky little curly E symbol, it comes from back when we did not understand very well what was going on in electricity. It stands for electromotive force, and I hate it because it's not a force. It's not measured in newtons. It's measured in voltage. So I'll use EMF or the symbol E, which is traditionally what's done in electronics and electricity. We'll say it's got an EMF of, well, your car battery has an EMF of 12 volts. Usually you're getting 11.5, 11.2, depending on what you're running through it. There is an internal resistance. There is the internal resistance. We want it to be small, and so Emily, to show that we want it to be small, it's traditional to use a lowercase r, little r, tiny resistor, tiny resistance. Sometimes, Alejandro, you'll see the internal resistance by the negative. Sometimes you'll see it after the positive. I kind of prefer it after the positive, and you'll see why. And often they'll do a dotted line around it to help you figure out that it's part of the battery. Let me show you an example here. This is from your review. There's the EMF, the maximum theoretical voltage. There's the internal resistance. You'll notice this one comes after the positive instead of before the negative. And they often put a dotted line around it to let you know that's the battery and that resistor is contained inside the battery. It should technically somehow be between the negative and the positive, right inside there, but that's too awkward to draw. Oh, and lowercase r, why? We want it to be small resistance. Okay? In my ski hill analogy, this internal resistance, how many of you have gone skiing before? When you get off the chairlift, is there not a short little hill that you ski right down, getting off the chairlift, a little bump, a little voltage drop, if we go to our height analogy? That's the internal resistor. It's like the little tiny bump that you ski down, the little 10-foot hill or 3-meter hill that you ski down getting off of the chairlift, which is kind of why I like to see it drawn here instead of here, but whatever. The only problem is this. Unlike in real life, the height of that bump can change. In real life, it can't, but in your circuit, it does. It all depends on what else is in the circuit. In fact, we're going to derive that right now. So in our ski hill analogy, the internal resistance is like the ramp at the top of the chairlift. It's like that little bump right there. As part of the ride to the top, there is inevitably a bit of a height loss on the ramp. You lose some energy, some voltage traveling through the battery in real life because batteries aren't 100% efficient. Oh, except this height can change, unlike real life. Example 1 says this. What happens to the cell voltage measured by the voltmeter if we close the switch? So all of us right now, let's add a little internal resistor to this battery. We're going to be more accurate. We're going to call it little r, lowercase r. And you're going to lose some voltage going through that lowercase r. Except I don't want to think of it in terms of voltage. What's the other way? What's the equation that we've used time and time again this unit where we've said there's another way to write voltage? What does V actually equal? Help me out. You're right. Someone said it there, didn't they?
V equals IR.
Cole, what?
V equals IR.
With authority, like you know what you're talking about. What?
V equals IR.
So I think the voltage drop going through the battery, guys, I think the voltage drop going through the battery would be total current, little r. Now, remember I said, though, Alejandro, that voltage drop, that hill at the end of the chairlift, the height changes. Let me show you why. If you close the switch, close switch. You may recall from lesson 5, we said when you add a resistor in parallel, the total resistance decreases, not gets bigger. When you add resistors in series, total resistance increases, but when you add them in parallel, you've opened up another ski hill. Some can go that way, some can go this way. The overall resistance has gone down. That means that your total current, well, if your overall resistance goes down and V equals I times R, what happens to your total current? It increases. So if the current flowing through the battery is total current, which is going to be in our circuits this year, we're not going to get any more complicated, and the current just got bigger, and the voltage that you lose going through the battery is I times R, what happens to the voltage that you lose going through the battery? Doesn't change, gets bigger, gets smaller. Sorry? Gets bigger. Now, by the way, little r if you want to go back to the previous page, internal resistance here, this is constant. This never changes. This is a physical component of the battery. It's based on some physical characteristic of the battery. It depends. It depends on what type of battery, whether it's a lithium or a carbon, or it depends on the chemicals in the battery, but it's a physical parameter of the battery deal. It doesn't change. You're stuck with your internal resistance once you've manufactured the battery. What does change is how much current flows through that battery. And because that voltage drop is given by current times that internal resistance, more current, lose more voltage, terminal voltage then, sorry, my bad, decreases. You lose more going through, your terminal voltage decreases. I circled increases, decreases. In other words, Dylan, let's suppose this was a 6-volt battery, and with the switch open, you get 5.8 volts when you actually measure it. You lose 0.2. When you close the switch, you won't lose 0.2 anymore. You'll lose 0.5 or 0.6 because overall current went up. Now, instead of measuring 5.8 volts, it's going to say 5.5 volts or 5.4 volts or something like that. So, as I total increases, IR increases, so we lose more voltage traveling through battery. Because we lose more voltage traveling through the battery, my terminal voltage, the actual voltage, it gets smaller. In fact, we can derive the equation for this all pretty easily. It says, find an expression for the terminal voltage if the cell supplies energy to the circuit. Well, your terminal voltage, V term, is equal to, before you plug the battery in, terminal voltage is equal to the EMF, the maximum, what it says on the side of the battery. You know what? Because no current's flowing. Hook up the current, and it's equal to the EMF minus, don't write this next bit down, voltage lost, don't write that down, voltage lost traveling through the battery, except what's another way to write voltage? Write this down. The current times the internal resistance. That's the equation. Although I got to be honest, Akemi, I hardly ever use this. I can derive this all from Kirchhoff's laws. Now, if any of you have your formula sheet, Kevin right now is saying, Mr. Dueck, that's not what my formula sheet says. Don't write this down. Kevin is correct. My formula sheet says plus or minus. That's going to be the physics of recharging a battery, which we're going to look at a bit later on this lesson. But right now, if the cell is the one that's supplying the energy, I'm telling you, if you were to stick a voltmeter on either end of the battery, you would not measure 6.0 volts. You'd measure 5.8 or 5.2. And it all depends. It varies because more resistance means lower current, means I get closer to my EMF. I lose less going through. Smaller resistance, if I removed a couple of these resistors, that increases the overall current. My battery isn't quite as efficient anymore. It gets hotter. A little weird. I said to you, Alejandro, I don't use this equation all that much. Let me show you what I mean. Turn the page. Yep. Example 3, Courtney, example 3 says, Find the terminal voltage. Mr. Dewick, there is a voltage on the battery right there, 20 volts. Yeah, I don't think that's the terminal voltage because that would make this a stupid question. You know what? I think 20 volts is the EMF. That's what's printed on the side of this battery. That's the constant voltage, the unchanging voltage, the maximum theoretical voltage that you would get in a perfect world. What do you really get in this circuit? Well, really what I'm going to do then is I'm going to solve everything in this circuit. And I always start up by looking for total current. Do I know total current? No? But I can tell you right now, psst, a little focus. No, seriously, a little focus. What's total resistance in this circuit? It's not 30. Can't be. I see other resistors there. Oh, because they are in series quite conveniently, aren't they? In fact, that internal one is always going to be in series for simple circuits. So I think the total resistance is 32 ohms. I guess that means I can find the total current, because that's going to be maximum theoretical total voltage divided by total resistance. It's going to be 20 divided by 32. 0.625? Okay. How many amps then are going through that 30 ohm resistor in the bottom? Really? Yeah, come on. Little feedback here. Oh, how many volts do we lose going through that bottom resistor? I times R. 18.75. How high is our chairlift? Are we in balance right now? Nope. Oh, how high must the little bump be at the end of the chair? How many volts must I lose going through here? Now, 1.25 volts. You understand, the other thing I could have done, Emily, is I could have said, you know what, there's 0.625 amps going through that internal resistor, and I could have gone I times R, and if you go 2 times 0.625, you know what you get? 1.2. I want to show you there's always two ways to get there now. We got ways to check our answers. So my maximum theoretical voltage is 20, but what's my actual terminal voltage?
18.75.
Or if I go to 3 sig figs, 18.8 volts. Now you'll notice I did not once use this equation. I used my Kirchhoff's laws, which that's my fallback. By the way, what this means is, Sebastian, up until now, up until lesson and including lesson 5, whenever I was giving you a voltage in a circuit, I was giving you this one here, the terminal, not the maximum EMF, because I was just rolling up the internal resistance drop into that voltage and just saying, oh, that's my net voltage, I'll use that. For what it's worth. What would happen if you changed this resistor? For example, what if it was 20 ohms? How would that change our total? Go down? How would that change I total? Go up? How would that change what you lost through here? You'd lose more. How would that change terminal voltage? Smaller. What if I put a bigger resistor here? What if I made that 40? Exact opposite. So what's constant in a circuit? The internal resistance itself, that's a physical parameter, and the EMF, that's also a physical parameter of the battery. Everything else, turns out, changes, depending on what your setup is. Example 4. Find the terminal voltage and find the internal resistance. Okay. And I don't think the terminal voltage is 50 volts, because that would make this a dumb question. That's the EMF, the maximum theoretical voltage. Okay. Oh! I said I always try and find total current. Holy smokes, they gave it to me. So what's the current in that 30 ohm resistor down there? 1.5 amps? What's the voltage that you lose going through that 30 ohm resistor right there? 45? Are we in balance? Nope. How many volts must we lose going through the chairlift, coming off the chairlift on the internal resistance? So first of all, what's the terminal voltage? 50, take away 5, 45 volts. That's what you'd actually be getting in this circuit when you measured it across the battery. Is that okay, Kevin? Oh, by the way, I know one more thing in that internal resistor. Not only do I know the voltage, 5, I know the current. What's the current flowing through that internal resistance, that little... Do I know 2 things in that internal resistor? Then I know 3. Oh, hang on. Don't use a capital R, Mr. Dewick. What do we traditionally use for the internal resistance because we want it to be small? R equals V over I, 5 divided by 1.5, which I'm pretty sure is going to be 3 1/3. There's one answer. There's another answer. And again, I didn't actually fall back, Kevin, to the equation on your formula sheet. I think in some ways that equation is redundant. The reason it's not is it's going to help us explain recharging the battery when there's a plus sign there in a little bit. By the way, look up for a second and have patience while my program loads. This really works better if there's not a big delay when I want to bring up Windows Journal. Come on. There we go. Circuit for you. .48 volts. What's the terminal voltage? It's got to be 48 because the only other resistor, the main resistor, this circuit only has one outside resistor. The only ski hill is 48 volts high, which I guess means the chairlift minus the bump at the end must have been 48 volts high. I don't know how, I don't know the battery. Could have been 50 volts, could have been 60 volts. Not likely, but it could have been. But as it turns out, I can get the terminal voltage in a single resistor circuit by looking at the voltage in that one resistor. Whoa. That wasn't good. Hopefully it continued working. Next page. Example 5 says, find an expression for the terminal voltage if the cell is being charged. Take a look at this diagram. What's weird about this diagram? What do you see? 2 batteries. This is a rechargeable battery system. What you have here is a larger voltage than what's in your battery. Let's suppose, don't write this next bit down, let's suppose this was 30 volts and this was 10 volts, but they're pointing in opposite directions. You know what your net voltage is? Take a guess. 20 volts. That's what this overall voltage would be. What we're really doing when we have a large battery, though, and here's where my ski hill analogy breaks down, current is going this way. We're actually somehow going down the chairlift. Although I guess you can ride a chairlift back down. So maybe my ski hill analogy doesn't break down quite as bad as I think. But we're going back down the chairlift, which means, well, it means that, write this down, your terminal voltage is the height of the chairlift plus the little hill at the end of the chairlift because you didn't ski down the hill. You went back up that little hill to get to the chairlift, and then you went down the chairlift. And in fact, it's this tiny little thing here, that's the little bit of extra voltage that's recharging your battery, which is why it takes so long to recharge batteries. This is the little bit of extra energy that the cell is getting to reverse the chemical reaction slowly and restore chemical energy in the battery. So although on one hand it'd be nice if batteries were 100% efficient, if they had no internal resistance, on the other hand we would be unable to recharge them if that was the case. So actually an internal resistance isn't that bad an idea, isn't that bad a thing. It's what gives us the unbalance. Yeah?
So then if it's just the IR, why do rechargeable batteries still fail after a while?
This is the mathematical recharging, but because it's a physical chemical reaction, the physical chemical reaction has a limited amount of times that it can continue to work, because when you recharge a battery, you don't get quite back to what you started from. There's always some chemical decay and breakdown. Yeah, we're back in our magic physics world where everything works nice. Certainly the lithium, they're pretty good. I think you get about 1,000 cycles off of a lithium battery. When I was in high school, in 1987, my physics teacher was talking, UBC was just announcing a breakthrough. They had just figured out how to make rechargeable batteries based on lithium. Up until then, they were all either nickel, cadmium, or carbon batteries, and they were terrible. Those ones only had a recharging cycle of about 80 or 90, and those were the ones that you had to drain all the way, because if you didn't drain them all the way, they would develop a chemical memory, and then they would only recharge part way and drain part way. They were finicky. They were not great. I mean, you used them because it was still cheaper, but cell phones wouldn't have been possible with the way that you can recharge them. Well, generally, the battery may not last the life of your phone, but it certainly lasts you a couple of good years of continuous recharging. So, example 6 says, find the terminal voltage if the cell is being charged. I suspect it's going to be bigger than 9 volts, otherwise this cell couldn't be being charged. I don't see a current anywhere, so my strategy is going to be, what's the total resistance? What is the total resistance of this circuit? 11 ohms. It could have. I just didn't bother including it. I think in your homework it does. I'm giving you the terminal voltage of the charger. It's a good point. In actual fact, it does. Probably this one is the internal resistance of the charger itself, and then we always add one resistor in the circuit, because if we add a resistor, that lowers the overall current. We don't want too much current on things to overheat. We want to just trickle charge it. And traditionally, that resistor is the little bulb that lights up when you charge. It's a great way to, oh, I can tell it's charging because the bulb went on, and conveniently, there's my built-in internal resistor, or external resistor to drop the current. Hey, what's the total voltage? If I got 30 volts in one direction and I got 9 volts in the other direction, what's my total voltage of this circuit, do you think? 21 volts. What's the total current leaving that 30 volt charger? .91 amps. So how many amps are going through this 1 ohm internal resistance of the battery? 1.91 amps. How many volts are going through that internal resistor of the battery? Dylan. Turns out it's my 1 times table, very convenient. 1.91 volts, except this time, because we're going in the opposite direction of the regular current, are you losing that voltage? No, this is a voltage gain compared to that battery. So the terminal voltage is 9 volts, but you're gaining 1.91 volts. What's your terminal voltage here? 10.9 volts. and it's that extra 1.9 volts that's doing the work inside the battery to reverse the chemical reaction, separate the charges again, and slowly recharge the battery, and that way it has that stored chemical energy again. Now, having said that, I'm fairly certain, Courtney, in your big ultimate review package, I don't think there's a single rechargeable battery. There might be one. I'm not going to throw rechargeables on your test, I don't think. I just think this is nerdily cool and interesting to know. And it certainly is a good reinforcement of Kirchhoff's laws and terminal voltage. So in summary, if we have one battery and it's supplying energy, V terminal is equal to the EMF, what's the constant maximum theoretical voltage, minus whatever voltage you lose going through the battery. Or, if we're recharging, it's the EMF plus you gain a little bit of voltage going through the battery. And Kevin, that's why it says plus or minus on your formula sheet. And having said that, I really only use this equation in the recharging. You'll notice, even though I showed you this equation, Kirchhoff's law most of it. We ski-hilled most of it. What's your homework? Here's what I assigned my block A's. Then I want to give you a tiny bit of advice, and then I'll turn you loose. No, that's lesson 5, Mr. Duke. Oh, lesson 7, okay. Homework. Number 1, number 3, 4, and 5. Now, here is my advice to you. I am not so good that I can just do these. I find I have to do a sketch. And it's also good practice. On your test, I'm going to give you word problems, some with no diagram. So for example, number 1, I would say I have a 6-volt cell with a little internal resistor of 0.6 ohms, and it's on a 7.2 ohm. And you'll notice my circuit diagrams, I'm kind of sloppy. I often don't even draw the symbols. I just put the numbers in sometimes, like I did on that bottom one. Once I have, and that's 6 volts. Now I think I can solve this okay just fine. You may, Vlad, be good enough to solve these in your head intuitively. Great. I find I have to do a sketch. So far, 1, 3, 4, 5, 7, 8, 9, 10, 11, 12. 1, 3, 4, 5, 7, 8, 9, 10, 11, 12. 1, 3, 4, 5, 7, 8, 9, 10, 11, 12. You got lots of time, well over a half hour. This is also a chance for a number of you that has a bunch of NHIs to get a bunch of stuff handed in, because I'll be probably doing a marks update tonight as well. Give me 1 second.